Okay, now it's time to do some exercises. So in all that follows, xs mu will be a measure space, and f any all functions will be real valued and measurable unless otherwise specified. But this is what, so I won't say it again and again. So this is a running hypothesis which we will have all the time. Okay, so first exercise. So xs mu measure space and fn a sequence such that every subsequence has a further subsequence which converges in measure and the limit f is independent of the subsequence. So let's understand this hypothesis. So you have a sequence, take any subsequence, then you can extract a further subsequence which will be converging in measure, and the limit function which you get there is independent. Whatever subsequence you are taking and further subsequence you are taking, the limit is always the same. It is independent of the subsequence chosen. Then fn converges to f in measure. So this is a very important property. If you have so for instance, if x tau is any topological space, this is a very useful, it's a very trivial observation for limits, but you should do this exercise. It take a couple of minutes, that's all, and it is extremely useful to know it. So x tau is any topological space, xn a sequence such that every subsequence has a further subsequence converging to a fixed point independent of the subsequence. And the limit is independent of the subsequence. Then xn converges to x. So you see, we can very often, using compactness arguments, we can extract subsequences which are convergent, but we'd like to know if the entire sequence converges. And if you can show that the limit is always unique in the sense that it doesn't depend, whatever may be the subsequence you started off, the limit is always a certain fixed element, then you can deduce that the entire subsequence will in fact converge to this point. So this is a very useful argument which we can exploit in very nice ways, and the same is true also for convergence in measure. Convergence in measure is not a standard type of convergence as we saw. It depends on some measures of some sets going to 0. And what we have here is the same property. If you have a subsequence and a further subsequence which converges to in measure to a limit f which is independent of the subsequence chosen, then the original sequence also converges to f. So this proof which I am going to do can be easily copied to do the general topological exercise which I have given here also. So assume Fn does not converge in measure to F. So what does it mean? That means there exists an epsilon positive such that limit n tending to infinity of the measure of the set of all x in X such that mod fn x minus fx greater or equal to epsilon is not equal to 0. The limit may not exist, limit is not equal to 0. Now, what do you mean that limit of some positive numbers is not equal to 0? That means you can, so this implies there exists an eta positive and a subsequence such that f and k such that the measure of the set of all x in X such that mod fn kx minus fx greater or equal to epsilon, this will be bigger than eta. And this will be true for any subsequence of this subsequence also. That means no subsequence of f and k can converge in measure to f, because this will always be bigger than eta and limit won't go to 0, and that's a contradiction to the hypothesis. Therefore, the original sequence converges in measure to f. Okay. 2. Xs mu measure space and fn goes to 0 in measure. Let an be a real sequence such that an decreases to 0. So it's a monotonically decreasing sequence whose infimum is 0. Then there exists a subsequence f and k such that for almost every x mod fn kx is less than ak, k sufficiently large. So it depends on x, of course. The k, how large, may depend on x. Okay, so solution. This is again application of the Borel-Cantelli lemma. So we are going to use the same argument. So E and M will be set of all x in X such that mod fn of x is greater or equal to am. Okay, so mu of E and M tends to 0 as n tends to infinity. M is fixed. Okay, so now since this goes to 0, there exists a nm, okay, such that mu of E nm m is less than 1 by 2 power n. Then sigma m equals 1 to infinity mu of E nm m is finite because it's a geometric series, so this is finite. Then there exists an E with measure of E equal to 0 such that on E complement every x can belong to at most finitely many E n m m. This is nothing but Borel-Cantelli. So if X belongs to E complement, there exists a capital N such that, of course, N may depend on X. For every K in K greater or equal to N, X does not belong to E n k k. That is, mod Fn kx is less than ak for all k greater or equal to n equals n of x. So that proves, so it's a very nice application again of the Burrell-Cantley lemma. Okay. 3. X S mu measure space Fn converging to F in measure for all n greater or equal to n in n, you have Fn greater or equal to 0 almost everywhere. Show that F is also greater or equal to 0 almost everywhere. So it's behaving very much like ordinary convergence. Namely, if you have non-negative functions, the limit in measure must also be non-negative almost everywhere. So, solution. So let En be contained in X, mu of En 0, and on En complement, Fn is greater or equal to 0. So you take E equals union En, n equals 1 to infinity, then you have mu of E equal to 0, and E complement is intersection n equals 1 to infinity En complement. Now Fn converges to F in measure implies there exists a subsequence Fnk such that Fnk converges to F pointwise almost everywhere. So let F contained in X, mu F equal to 0, and Fnk of X converges to F of X for every X in F complement. So now you said G equals E union F, mu E is 0, mu F is 0, so this implies mu G is 0. And what is G complement? That is E complement intersection F complement. So on F complement means everything goes to 0. So if X belongs to G complement, you have Fnk of X converges to F of X, and Fnk of X is greater or equal to 0, and this implies Fx is greater or equal to 0. That is, except on G which just measures 0, that is F is greater or equal to 0 almost everywhere. Let me call this A. B. Deduce that Fn converges to F in measure, Fn less than or equal to G almost everywhere implies F equal to G less than or equal to G almost everywhere. 1. 2. Fn converges to F in measure, mod Fn less than or equal to G almost everywhere implies mod F less than or equal to G almost everywhere. So solution immediate. So Fn is less than or equal to G. So G minus Fn is greater or equal to 0 almost everywhere, and G minus Fn converges in measure to G minus F, and then the result follows. Similarly, mod Fn converges to mod F almost everywhere, and so this is 1. Now result follows from A. then mod fn converges in measure to mod f, and you have mod fn less than or equal to g almost everywhere, implies mod f less than or equal to g almost everywhere by 1 above. For x s mu measure space, fn converges to f in measure, fn less than or equal to fn plus 1 for all n. Show that fn increases to f almost everywhere. So solution, let g equals sup over n fn, then fn less than or equal to fnx less than or equal to fn plus 1x for all x for all n, implies fn increases to g. Okay, so to show f equal to g almost everywhere, so that would do the trick. But fn is less than or equal to g implies that f is less than or equal to g almost everywhere by 3 b1. Now fix n in n. Consider the sequence f n plus k, k equals 1 to infinity. Then that's a subsequence, and therefore fn plus k also converges in measure to f. And you have fn is less than or equal to fn plus k for all k, and this implies that fn is less than or equal to f for all n. So this is true. Okay, now true for all n. This implies fn is less than or equal to implies g, which is a supremum, is less than or equal to f. Okay, and this implies that g less than f, f less than g implies f equal to g almost everywhere. Okay, so we will stop with this, and next time we will start integration.